All right, so we have parametric curves. Yippee-yi-yo-ki-yay. What does that mean in a calculus course? Well, we can do a lot with parametric curves from a calculus standpoint. Consider the following. Here's what the chain rule says. The chain rule says that if I have the derivative of y with respect to x, and I multiply that by the derivative of x with respect to t is our brand new parameter, that is the derivative of y with respect to t. Thus, if I want the slope of a parametric curve, I just take the derivative of y with respect to t and divide it by the derivative of x with respect to t. Done. Similarly, if I want the second derivative of y with respect to x, I take the derivative of y prime with respect to t and divide by the derivative of x with respect to t. So whatever answer this is, I take the derivative of that and stick it there. Okay? The derivative of this and stick it there to get a second derivative. I'll show you what I mean. For the curve, x is 4 cosine t, y is sine t, and we looked at that in our last lesson, so we know what this looks like. Find the equation of the tangent at time equals pi over 3. So, if I'm looking for the equation of the tangent, I know how to find the equation of a tangent. That's y minus y1 equals x minus x1 multiplied by the slope. So how do I find those pieces? Well, the x value is 4 times the cosine of pi over 3, right? We just write in there, and that's okay. And then the y value is the sine of pi over 3, and I know what that is. So time for slope. How do you find slope? Well, dy dx is the derivative of y with respect to t over the derivative of x with respect to t. Well, the derivative of y with respect to t is cosine t, and the derivative of x with respect to t is negative 4 sine t. So we want to evaluate that at pi over 3, and that's 1/2 over negative 4 square roots of 3 over 2, and that turns out to be negative 1 over 4 root 3, and that's what goes in that slot. So I get the equation of the tangent lickety-split. Lickety-split. If x is t squared plus 2 and y is t minus 2, again, we've taken a look at this. Find dy dx at 3, negative 1 and at 2, negative 2. So, I mean, I know what I'm doing here. I know that, generally speaking, dy dx is the derivative of y with respect to t over the derivative of x with respect to t. Here's the problem. I don't know what t is here. I don't know what t is here. Oh, wait, yes, I do. This will help me know what t is. This will help me know what t is. And now I look at my slope and I say, at this point, dy dx is 1/2. And at this point, dy dx does not exist. There's a vertical tangent at that point. And if you remember the picture from our last lesson, it is true. There is a vertical tangent at that point. I'm going to go one more. Find the second derivative of y with respect to x in terms of t for the curve where x is 4 minus t squared and y is 6 plus t to the fourth. And just to show you how that all holds together, dy dx is the derivative of y with respect to t over the derivative of x with respect to t. And that turns out to be negative 2t squared. So when we go to find the second derivative of y with respect to x, the denominator is still dx dt. The numerator is the derivative of this. Boom. Okay, the numerator here is the derivative of my dy dx in terms of t. So just from a crank it out perspective, that's important. Small shift here. Here's a side note. La. A curve has a horizontal tangent if dy dt is 0 and dx dt isn't at that point. A curve has a vertical tangent at a particular point. I mean, a curve has a horizontal tangent at a particular point if dy dt is 0 and dx dt is not. A curve has a vertical tangent at a particular point if dx dt is 0 and dy dt is not at that point. If dy dt and dx dt are both 0, then it's tricky to figure out if there's a horizontal tangent or a vertical tangent or neither at that particular point. So find all horizontal and vertical tangents to x equals t squared minus 2t and y equals 2t cubed minus 3t squared. Okay, I can do this. I can do this. I know that dx dt is 0 when... Oh, that's so wrong. Take the derivative of x with respect to t. I can do that. T is 1. When is dy dt 0? Well, dy dt is 0 when this is true. That's true for 2 values of t. So there's a horizontal tangent when dy dt is 0 and dx dt isn't. At t equals 0. And if t equals 0, y equals 0, and that's the horizontal tangent. Vertical tan? Not so much. Not so much. There are no vertical tangents. Now you're saying, wait a second, Sparky. Wait a second. I can graph this sucker. I have technology. T squared, oh, caps lock. T squared minus 2t, and this is 2t cubed minus 3t squared, and we'll just graph the, oh, really? And we'll just graph this on, okay, so we're going to try this one more time. T squared minus 2t, and this is 3 t squared, no it's not, it's 2t cubed minus 3t squared, and we'll do this on a very small interval of x values and see nothing because we're still using the other window. This. This is the point where time is 0. Nice flat horizontal tan. This is the point where time is 1. Not a horizontal tan, not a vertical tan. A weird cusp. Okay? Okay. Which brings us to our first OYO of this lesson. Here is our first OYO for this lesson. Want to find all horizontal and vertical tans if they exist for the curve x equals t minus e to the t and y equals 2 plus e to the t for all possible values of t. That's just something to think about. I want to spend a little bit of time, not much, a little bit of time, talking about vector motion. Because it's next to impossible to take a look at a picture like this and not imagine a particle moving over time. Time equals 0, time equals 1, time equals 2, time equals 3, and so on. It's almost impossible not to imagine a particle moving along the curve. So when a parametric curve models particle motion, we may speak of some things with respect to the particle. We can talk about the particle's velocity vector. In the plane, when there's only one variable in play, we talk about velocity. Velocity is a number. When we do this for a parametric curve, velocity is a vector. Sometimes we use the funny brackets like this. Sometimes we use parentheses around the outside instead. Context will make it clear if we're dealing with a vector or an ordered pair. The velocity vector is just x prime, y prime. As you would expect, a velocity vector, the x component has a velocity, the y component has a velocity, and that determines the velocity vector for the particle. The side note here, speed. Speed is always the magnitude of velocity. Well, how do you find the magnitude of a vector? Square 'em, add 'em, take a square root. Square 'em, add 'em, take a square root. So if I want the particle's speed at time equals 3, x prime of 3 squared plus y prime of 3 squared, take a square root. We may also speak of the particle's acceleration vector. The particle's acceleration vector, and that's just x double prime of t, y double prime of t, nothing fancy there. Okay? One other thing. We can talk about how far a particle has traveled. So if I were to ask, start at time equals 0, go to time equals 2, if I were to take this part of the curve on a string, pull it taut, and measure the string, how far would the particle have traveled? Well, that just takes speed and integrates it over time. So arc length is an integral from your starting time to your stopping time of speed. It's just the integral of speed. So some things to consider for you. Some things to consider. If a particle is moving such that x is t squared minus 2t and y is ln t minus t, when is the particle at rest? That's an interesting question. And what is the arc length of the curve where x is cosine t and y is sine t on 0 to 2 pi? This question can be done without a calculator. This question could in theory be done without a calculator, but you'll probably use one for it. Those are some things we should talk about when we gather. I'll also have some nice questions for us to consider when we gather as a group, and I look forward to it, and I'll see you then.